Hello everyone, my name is Stanislav Krulik and I am third year PhD student at Skolkovo Institute of Science and Technology, Moscow, Russia. In this talk entitled Security Issues in Distributed Storage Networks, I would like to present you the second part of my PhD thesis, which I do under supervision of Professor Alexey Frolov and Professor Grigory Kabatyansky. So let me start with small motivation. Now we are living in information world and total amount of data stored by humanity grows every day. So people typically move to distributed storage system and distribute their data among servers located in different physical locations. Unfortunately, servers typically can be not available, and system designers move their attention to error correcting codes in which they introduce some redundancy to stored data in order to effectively recover temporarily or permanently unavailable data. And in first part of my PhD thesis, I focused on one kind of such codes called locally recoverable codes. In local recoverable codes, each node is a function of small amount of our nodes. And in case of node failure, we just connect to the corresponding subset of our nodes and easily recover temporarily unavailable data. In first part of my PhD thesis, I worked on some generalization of locally recoverable codes motivated by application to the hot data, which with the generalization called local recoverable codes with availability. And in case of local recoverable codes with availability, each server have different non-intersecting subset of our nodes, which can be used to recover it. So in such a case, we can proceed the recovery procedure in parallel mode. Another classes of code for distributed storage are called regenerative codes. In such a case, each server stores some big string, some subset of big symbols, and in order to recover temporary unavailable nodes, we connect to many servers in such a system and download just a small portion of data or some function of data stored in this server and accomplish the recovery procedure. In the case of regenerating codes, there is a well-known cut set bound. I move my screen to the now part of the slides. So cut set bound is presented here, and it connects the total amount of data stored in such system B, amount of data stored in each server alpha, amount of server to which we connect in order to make a recovery procedure, and beta, number of symbols which we download from each of these servers to which we connect in order to recover temporary unavailable data, and k is a number of servers to which we have to connect to download all B information symbols. So there's a trade-off between storage and bandwidth, and in case when we minimize storage, we work in MSR point. In case when we minimize the bandwidth, we work in MBR point. These points are presented in this graph. So unfortunately, the majority of papers focused only on security issue, only on effectively recover of temporary unavailable data, and don't focus on the security of stored data. Unfortunately, when we work with distributed storage, we have a lot of servers, we have a lot of users which work in such a system, and so our data are very vulnerable to attacks and data leakage. So the main goal of the second part of my PhD thesis is to design codes which supports the effective recovery of temporarily unavailable node while preserving resistance against eavesdropper. So typically, security issues in distributed storage systems can be solved by means of computational cryptography. But unfortunately, based on the information provided in this journal article, the computational cryptography becomes irrelevant while growing of nodes in our system due to the problems of key management as well as high communication and computational overhead. The solution is to use information theoretical security. When we add to our useful information some amount of random noise, somehow mix them and ensure what mutual information between content available to eavesdropper and useful information are zero. So our eavesdropper gains no information about stored data. Let me move to a system model. In our system model, we encode a set of B symbols over some finite field with Q elements into n multiple by alpha symbols what form n by alpha code matrix C by means of storage code with generated matrix G. So in other words, we make some linear transformation of our B information symbols. And each of n nodes of our distributed storage systems corresponds to one row of matrix C. And in case of locally recoverable codes, we assume that each node stores one symbol. There are two main approaches to ensure the security of distributed storage system. First one is to precode information in random symbols by maximum rank distance code. For example, Gabardinian codes. Despite this approach can ensure security for a large range of storage codes, the required field size is exponential with number of nodes, what makes direct practical application difficult. Another one is direct mixing of information and random symbols using the storage code. Although the size of the field is governed by storage code and hence can be even binary, it is not clear is this approach applicable in general case of nodes. In this paper, we consider two different types of eavesdropper and note what both eavesdropper are passive, what means what we can change the node content. And the first eavesdropper model, which is very common and is presented in many scientific papers, the eavesdropper can observe all data stored on some subset of nodes as well as data transmitted to accomplish repair of some subset of nodes, which corresponds to the case when our eavesdropper fully controls some subset of nodes in our system. For example, it can control some data center involved in a big distributed storage system. In our paper, in my PhD thesis, I propose to consider another type of eavesdropper, what can observe small portion of data from all nodes. This corresponds to the case when eavesdropper controls the communication infrastructure of our distributed storage system. So he can access small portion of data from each node insensibly, and after he observe, he download a lot of data, the user can be aware what someone download its data and can somehow punish the guy who do it. And these models coincides in case of locally recoverable codes, but let me show the difference. So let me consider the following distributed storage system with three nodes. Z1 and Z2 is random noise, and A is our useful information. All the data are binary, and addition are done on model 2. This system can be seen what this system is secure against first eavesdropper. So let eavesdropper can access node 1. So he download just two symbols of noise. But if eavesdropper can download two symbols but from different nodes, for example, one symbol from one node and one symbol from another node, he can easily extract the useful data. For example, he can download from node 1 Z2 and from node 2 Z2 plus A, and just sum with downloaded bits and receive the useful information A. So this system is secure against first eavesdropper and don't secure against the second type of eavesdropper. But first of all, I considered the security of locally recoverable codes in which these two models are coincides. and published paper in last year VTC fall. And to ensure the security of locally recoverable codes, I extend the approach proposed by Agarwal and Mazumdar and directly mix information and random symbols by MRD-based locally recoverable codes. And I generalized their approach to the case of locally recoverable codes with availability or different non-intersecting recovered sets for each symbol, and achieve the construction and which approach the following bound on the amount on information symbols stored in such a system. So B is total amount of information symbols stored in such a system. M is number of nodes sufficient to recover information symbols. L is number of nodes available to eavesdropper. And R is a number of symbols to which our user have to connect to recover temporarily unavailable node. Also, I considered the security of originating codes in which two eavesdropper models are different and propose the construction which is secure against the second type of eavesdropper. So first of all, I modify the cut set bound and find the maximum amount of data which we can store in such a system to ensure the security against eavesdropper with limited access to all nodes, and propose an explicit construction of MBR array codes based on the simple idea of augmenting code matrix C with random matrix Z of corresponding size and multiplying obtained matrix by Van Dremont type matrix to distribute noise. This paper was accepted to NITR 1 conference and will appear in its proceeding, I hope, in October or in November this year. So in further research, I will try to find an explicit construction of MSR regenerating codes, which is secure against the second type eavesdropper, and consider the hybrid eavesdropper model with full access to small portion of nodes and limited access to remaining nodes. Propose and bound on the amount of data which we can securely store in such a system, and propose an explicit construction of codes which is secured against such an eavesdropper. So that's all. Thank you for your attention. If you have any question, please ask them during the PhD forum session or address them to my email. I will be glad to answer them. So thank you one more time. Goodbye.